So the chapter 1 homework on WebAssign is due today. The chapter 21 homework will be due in a week on Thursday the 5th. Anything else? And your grades for the first quiz are posted. They should have been posted yesterday, but apparently when I switched to Ultra, they added an extra step in the way grades post, and so I had to say yes to additional things that I didn't realize I had to do. Sorry, so they were up, and I loaded them yesterday, and then I checked this morning, and there was a thing I needed to do. So they're visible now. You can see your grades on the quiz. Most of you did reasonably well. The average was in the 80s. So I will continue. Oh, and if you'd like to see your quizzes and see what you got wrong, you can come visit me during office hours. I'm keeping them in my office, but I won't be returning quizzes. So we were talking about earthquakes. Now, one of the most dangerous kind of earthquake is a submarine earthquake. And the reason that submarine earthquakes are particularly dangerous is because they can cause tsunamis. And tsunamis can be incredibly destructive. So a tsunami is an enormous wave caused usually by an undersea earthquake. Not always. You can have tsunamis created by large landslides, volcanic explosions, things like that. There was a smaller in scale, but really interesting tsunami that happened a little while ago, where there was, I think it was a glacier collapse. So basically it was a landslide, but it created a tsunami in this like fjord, this sort of valley. And it basically resonated back and forth in this valley fjord for like weeks. The wave just kept going for a few weeks, bouncing back and forth in this valley. But tsunamis caused by large undersea earthquakes are some of the most devastating examples. The recent tsunamis in Indonesia have been particularly destructive. And they were caused by earthquakes just off the coast. So if the source of a tsunami is far away, there are systems out there to detect and predict and tell if a tsunami is on its way. Because it's a wave, it travels across the ocean. So the US and Japan have set up a bunch of sensors out in the Pacific Ocean to detect the waves as they travel across the Pacific Ocean. But if the earthquake that causes the tsunami is just off the coast, you don't have any time. That's what happened in Indonesia. It's also what led to the Fukushima disaster, was where there was an earthquake that caused a tsunami, and then the tsunami hit a nuclear power plant.
There are more tsunamis in the Pacific Ocean than any other. So in 2004, the world was taken by surprise when one of the largest recorded tsunamis of all time took place in the Indian Ocean. On December 26, 2004, Indonesia was rocked by the second largest recorded earthquake ever, 9.2 on the Richter scale. Minutes later, a 90-foot tsunami slammed into the Southeast Asian coastline. 225,000 men, women, and children lost their lives.
The Indonesian earthquake had as much energy in it as the total energy consumption in the United States in 1 year.
This enormous burst of energy had been released in just seconds. Once again, the world had been reminded of the Earth's awesome power. In the last 50 years, scientists were finally able to confirm a solid link between earthquakes and tsunamis. Although the Earth may seem to be a solid sphere, beneath the oceans and continents it is divided into 8 major and many minor segments known as tectonic plates. Where they meet, they can grind and jostle against each other at fault lines, causing earthquakes. Geologists had long thought that the Cascadia fault line was incapable of generating a major quake. But Atwater's investigation has proved that it was highly active. The big worry for Atwater and the thousands of people who live in this region is that the Cascadia fault line bears an uncanny resemblance to another highly active fault line, the Sunda megathrust. It was an earthquake along this fault that was responsible for the Indian Ocean tsunami that killed nearly 250,000 people.
Where we get 2 tectonic plates coming together, such as in the case of the Indonesian tsunami in 2004, one plate pushes beneath the other plate and creates lots and lots of friction and tension and drags the upper plate down with it. And that process can take hundreds of years, even thousands of years. It's a very slow process. But eventually, the pressure of this one trying to push back up again wins, and it flips like that. And that creates a megathrust, a sudden movement of the seabed. And that's what creates a phenomenal tsunami.
So tsunamis can be devastating and destructive. So if you live in a place where tsunamis are relatively common, there are steps you can take into account to deal with them. Like there are ancient markers in Japan that basically show build all your houses above this line because the tsunamis go up that high. And they basically marked along coastlines, like just up to this point, stuff is going to get wiped out. So let's talk about how the crust can deform and form mountains. So we mentioned there's this 3 ways the plates can interact. They can spread apart, come together, or slide against each other. And when they come together, that is a way, especially if you have continental crust running into continental crust, nothing can sink, so stuff buckles and you form mountains. So along plane boundaries, tremendous forces can be exerted that result in the buckling, fracturing, and shifting of units of rock. These can rupture the plate edges into huge displaced blocks that can eventually result in the formation of mountain ranges. And there's 2 basic forms of deformation to the crust that can occur. These are folding and faulting. Folding is when the crust bends, and faulting is when the crust cracks and slides along the crack. Generally, faulting happens more near the surface, folding happens more deeper down, because compressed, hotter rock is more plastic, while less compressed, cooler rock is more brittle. And what can happen is you can have folding first and then faulting after, once you overcome the ability of the rock to deform. The folding is the buckling of the rock layers into anticlines, arches. So anticlines are curved up, and synclines are troughs. They're curved down. So folding occurs when you have slow forces, relatively. Slow compressive forces that apply extreme pressure on the rock layers, and they cause the rock to fold, bend. Like if you take a piece of paper and you push on it, it bends. Same thing, just with layers of rock. Or if you take a lump of Play-Doh with layers in it and you squeeze it, it will bend and fold. Now, the forces that cause folding can be exerted either horizontally or vertically. And in general, folding occurs mainly during the early stages of mountain building. Basically, first rock will fold until the forces get too strong, then it'll start to crack and slide along the cracks. So crustal folding in an extensively folded area, the folds don't necessarily correspond to the terrain you see at the surface. It's a particular rock layer's resistance to erosion that determines what kind of topographic feature on the surface is formed. So anticlines, where it folds up, don't always form high ridges, and synclines don't always form little valleys. So the surface pattern doesn't necessarily match the underlying folding pattern. One of the best ways to see rock folds and faults and other things actually is road cuts. So if you've ever been driving along and gone through a road cut where they cut a slot for the road to travel through, done a lot of those around here because it's really freaking flat. But if you travel further west or further east, you'll see them. Sometimes, they cut through a hill. And when they do that, well, they cut through a hill and you can just see a slice of the rock. And so you can see the internal layers. Now, the other way that the crust can deform is that instead of bending, it can break. It can fault. And a fault is a crack in the rock where there's been visible movement of the two sides. If there hasn't been visible movement and there's a crack, it's called a joint. That's the only difference between a fault and a joint. A fault has moved, a joint hasn't. So a fault is a fracture in the rock in which there's been visible movement of the two sides relative to each other. Now, the stresses that can form faults can be either compressional. You can squeeze things together, and what will happen is you'll have two blocks, and one will slide up on top of the other one. Or they can be tensional. You can pull things apart, and you'll have two blocks, and one will slide down the other one. So in compression, if the compression is vertical, you get uplifts, where you get areas that are thrust upwards. This happened to the Colorado Plateau, for example. So the whole area around Colorado and such, with the Colorado River and the Grand Canyon and all of that, that whole area was pushed upwards, and it led to some really impressive things like the Grand Canyon, because what happened is that there was existing rivers and stuff, and they stopped doing lowland river things of flowing sideways and just started digging straight down. And so you got some really impressive geological structures from that. If the compression is horizontal, the crust gets shortened. And you can also have tensional or pull apart stress that forms faults. This causes the crust to lengthen. And you're going to have faults that slide shear side to side as well. So for faults, all the fault terminology pretty much there's some funny terminology because most fault terminology comes from mining. Because one of the places that valuable minerals or valuable resources get deposited is in faults. Because basically water with things dissolved in it will seep along faults, deposit material. And so if you're looking for valuable things, you'll mine along the fault line to track like a vein of gold or a vein of some other valuable mineral. So a fault plane is the approximately planar surface along which the actual movement takes place. That's the crack. It's the actual flat plane of the crack that's on which things are sliding. Now, there's two sides to a fault. And they're defined, there's a top one and a bottom one, because that fault plane is almost never perfectly vertical. It's usually at some angle. So the hanging wall is the fault block that's on the uppermost side of an inclined fault plane. It's called the hanging wall because when you cut a mine through here, it's where you hang all your stuff because it's your ceiling. And the footwall is the fault block that's on the lower side. It's called the footwall because it's the one you're walking on when you cut a mine through. So hanging wall is the top, footwall is the bottom. And the block that moves up relative to the other side is termed the up-thrown side. So if forces are compressional, the up-thrown side will be the hanging wall. The whole thing will get shorter. If forces are tensional, the up-thrown wall will be the foot wall, and the whole crust will get longer. So there's three basic types of fault depending on the direction of the sliding. These are normal, reverse, and transform. A normal fault is what happens when you stretch the crust out, pull it out. The hanging wall slides down the foot wall, the crust lengthens. These are caused by tensional or pulling apart forces. The normal faults are what happens when you pull the crust apart. Reverse faults are the opposite. They're when the foot wall moves down with respect to the hanging wall moves up the foot wall. These are caused by compressional forces, when you're squeezing the fault together. And then strike slip or transform faults are when instead of moving up or down, you move sideways. You slide sideways along parallel to the fault plane, horizontal motion. And technically there's a fourth type that we're not going to talk about called the dip slip. That is a combination of normal and reverse and strike slip. Stuff goes in an angle. But we're not going to talk about it. These are the three main types. We're also going to mention this special type of reverse fault. So a particularly shallow reverse fault causes a significant amount of older layers of rock to end up on top of younger layers of rock, and it's called a thrust fault. So this is a thrust fault. It's just a reverse fault that is very shallow. It just has some pretty unique geology when you're digging down, which is why it gets a special name. And in the last video, they mentioned in the tsunami video, they mentioned a mega thrust fault. That's just a really big thrust fault that's caused by subduction. So here's the fault, the foot wall, the hanging wall, the fault plane. If the hanging wall slides down and the foot wall goes up, that's a normal fault. The cliff formed is called the fault scarp. If the foot wall goes down and the hanging wall goes up, that's a reverse fault. If a reverse fault is particularly shallow, it's called a thrust fault. And what you get in the thrust fault is you get older layers of rock on top of younger layers of rock, which is a weird thing that stands out. And then lastly, if it goes side to side, it's called a transform or a strike slip fault. So here's a video about the various types of faulting and folding and the appropriate.
Hello everyone, this is Earth Science teacher Tim Martin, and in this video I want to introduce you to the geologic concepts of folding and faulting. When we look for faults and folds in the Earth, what we're really doing is looking for past evidence of plate tectonic motion. Let's take a minute to review the basic motions of plate tectonics. The first of the three motions is divergent motion. This occurs when magma comes up from deep within the Earth. This typically happens in the middle of the ocean. It generates earthquakes as the plates move apart from each other. This may also happen on continental plates as well. The next type of motion, convergent motion, happens when plates collide. Here we can see an oceanic plate subducting beneath a continental plate. As the plate subducts, it cracks and breaks, generating earthquakes. Finally, we have transform motion. This occurs where two plates slide or grind past each other. Again, this generates earthquakes. Now let's take a look at the structures identified with each of these three types of motion. To start off with, let's talk about rifts or cracks. When the Earth is pulling apart or forces are acting on it in opposite directions, the crust will thin, stretch, and possibly crack. These cracks are often known as rifts. This is caused by tension or divergent motion. A normal fault also happens with tension or divergent motion. If the rock is more rigid and less likely to stretch, it may simply crack, and when it does, one block may drop lower than the other. This is what's called a normal fault. Opposite the normal fault, we have a thrust or reverse fault. This occurs from compression or convergent motion. When two plates are pushing against each other, one plate may go down or another one may go up. This creates a thrust or reverse fault. Finally, a transform fault or a strike-slip fault occurs with lateral stress. When two parts of the Earth's surface are moving in opposite direction with respect to each other, one may slide, causing a transform or a strike-slip offset. While sometimes rocks break with faults, sometimes they're soft enough to fold. A fold occurs with compression or convergent motion. Sometimes rock layers may fold with an upward bend, other times they may form with a downward bend. Both types of folds occur with compression or convergent motion. An upfold is referred to as an anticline. The downward or U-shaped fold is referred to as a syncline. Let's take a look at what this looks like with real geology. Can you identify the motion from these real images? Let's take a look at these 5 different features. Thingvellir National Park in Iceland is one of the classic locations where the Earth is splitting apart. On the right-hand side of the picture, we see the North American plate. On the left side, the European plate. As the plates are splitting apart, this rift or gap is opening up. This occurred through divergent motion. This picture of the Hayward Fault was taken in Fremont, California, in Central Park. You can see when the road planners built this road, they didn't intentionally offset the sidewalk and curbing. What happened here is part of the road was built on the North American plate, and the other part of the road was built on the Pacific plate. Here's the fault line, and we can see the further section is moving northward, where the side that the photographer is standing on is moving towards the south. Moab Fault is a dramatic fault that was revealed in a road cut just outside of Arches National Park in Utah. Here we can see several very large faults. As we identify the previously aligned layers, we can see that this brown stripe used to all be the same layer, but now has been offset with several normal faults. This represents divergent motion or tension. Browns Canyon of the Arkansas River goes through Salida, Colorado. Here we can see rock layers that have been folded. This must have occurred through compression or convergent motion. It's impossible to make a fold by pulling. Going from a large scale to a rather small scale, in Mosaic Canyon in Death Valley National Park, California, we can see this small layer was offset. The fault indicated in red, and these yellow layers are offset with a little bit of overlap. This indicates that this was a reverse fault caused from compression or convergent motion. So let's take a little quiz. Can you identify the motion in these next 5 images? Feel free to pause the video between each image. Number 1 is Katobe Knob, located in the Cedar Mountain Recreation Area in the San Rafael Swell in Utah. Number 2 is a rock structure that I found at Noosa Heads in Queensland, Australia. Number 3, a road cut near Orderville, Utah. Number 4, rock layers west of Wild Rose Campground on Wild Rose Road in Death Valley National Park. Number 5 is specifically called Earthquake Fault, located just outside Mammoth Mountain Ski Area in Mammoth Lakes, California. So, could you identify all 5 of these images? What sort of plate motion caused each? Are they normal faults, reverse faults, folds, or rifts? Let's take a look at each. Number 1, Katobe Knob in the San Rafael Swell in Utah. First, we identify the fault plane, located here. Then we identify the layers that used to line up, here and here. So we can see, because of the overlap, this must have formed from compression or convergent motion. Number 2, Noosa Heads in Australia. Again, the first thing to do is identify the fault plane, located here. Then the layers that as they used to match up, here and here. Because of the lateral offset, we understand this must have been transform or a strike-slip fault. Number 3, again, this is a road cut in Orderville, Utah. Let's identify the fault plane, leaning from left to right across the image. See the double brown lines towards the bottom of the image? These used to match up with each other. Thus, this is a normal fault, formed through tension or divergent motion. Number 4. Along Wild Rose Road in Death Valley National Park. We can obviously see folds. These folds must have formed from compression or convergent motion. Finally, number 5. The earthquake fault near Mammoth Lakes, California. Again, this is a great example of a rift where the earth was experiencing tension and cracked open, causing this split in the rocks. Would you like a little more practice identifying folds and faults? You can download a slideshow of images that I've taken from around the world of places where we can see convergent, divergent, and transform plate motion. Thanks for watching, and I hope to see you.
So, Kai, right? Okay. Mountain building primarily happens occurs along converging plate boundaries, where crust is coming together. That is where you're most likely to have mountains being formed. If you're sliding side to side, you're unlikely to create anything. And if you're spreading apart, that's less likely to make things bigger. It's going to make things, it causes rift valleys and seas. Now, mountains can be classified into 3 broad categories based on their characteristic features. You're going to have volcanic mountains, mountain ranges that are caused primarily by volcanic processes, fault block mountains, mountain ranges that are caused by big faults forming and blocks of material tilting on their side, things like that. And you're going to have fold mountains, mountains caused by compression and folding. Volcanic mountains are primarily formed through a series of volcanic eruptions. Lots of the island chains out there are volcanic mountains. Most volcanic mountains are located along convergent boundaries because the subducting plate will melt and cause significant amounts of volcanic activity, forming actual mountains. So along an oceanic convergent boundary, you get chains of volcanic islands that form on the plate overlying the subduction zones. So things like the Aleutian Islands of Alaska, that long chain of islands off, the dangling lower eastern edge of Alaska, Japan, the Lesser Antilles, much of the island chains in the Pacific are volcanic mountains, formed at convergent boundaries. And volcanic mountains could also form at continental oceanic convergent boundaries. Because the continental plate will always overlie the subduction zone, the mountains will form on the continent. These mountains, you can get ranges of mountains that their core is often large quantities of volcanic material that never actually necessarily made it to the surface. But you do get lots of volcanoes in them as well that build up mountains. So the classic example of this is the Andes Mountains of South America. This process of mountain building at a continental oceanic convergent boundary is traditionally called Andean mountain building. These are formed as the oceanic Nazca Plate gets subducted beneath the continental South American plate. So there are both large-scale structures of igneous rock underground in the Andes, but also there's plenty of volcanoes along the Andes as well. And the Cascade Mountains of the Pacific Northwest are also volcanic mountains. And you get nice, big, dramatic volcanoes like Mount St. Helens, Mount Hood, things like that. The most destructive volcanic eruption in the US was Mount St. Helens when it blew its top. So here is some volcanic mountains in the Cascades in Washington. Fault block mountains are occurred actually when you have normal faulting. So what can happen with normal faulting when the crust is spreading apart, these big blocks get separated apart, they can actually tip over on their sides. And you can get mountains formed by the tilting and uplift of large crustal blocks. And this can result in dramatic fault block mountains that rise abruptly above the surrounding lowlands. So the Grand Tetons of Wyoming, the Sierra Nevada mountains of California, and the Wasatch Range of Utah are all examples of fault block mountains in the US. So here's Mount Whitney. This is sort of asymmetric shape, like steeper on one side than the other, at a very sharp corner. Now, fold mountains are mountains that are characterized by the prolific folding of the rock strata. This is what happens when two continental plates run into each other, they buckle and fold. So for the youngest mountains in the world are the Himalayas, which are still being upthrust and folded by the impact of the Indian plate into the Eurasian plate. The Alps are also fold mountains, and the Appalachians are fold mountains in the US. They're very old mountains. They were formed when Pangaea formed hundreds of millions of years ago. So these mountains are also categorized by thick packages of marine sedimentary strata because they formed when an ocean closed up as two continents merged, and that process basically scrapes all the marine sediment off the bottom, and it piles up in between the two continents until they collide. And since all that marine strata is in the middle, it gets pushed up and stuck on top of the mountains. So this stuff was originally deposited below sea level, and then it got uplifted and incorporated into the fold mountains. So for example, you regularly find marine fossils high in a fold mountain range. The tops of the Himalayas, for example, are covered in marine fossils. So you can go to the highest place in the world and find stuff from the bottom of the ocean. So here are some examples of fold mountains in Alberta, Canada. You can see the folds here, and the actual strata there. The Rockies are also primarily fold mountains. So the Himalayas, these are the youngest fold mountains. These are the youngest mountains in the world in many ways. So during the breakup of Pangaea, about 200 million years ago, the subcontinent of India broke away from Africa. And as the Indian plate moved north towards Asia, oceanic lithosphere continually subducted beneath Eurasia. And during the time before the continental collision, various sediments were deposited on that ocean floor between India and Asia, in the marine waters between them, because there's a constant deposition of sediment in the ocean. Stuff lives, material constantly settles to the bottom and gets deposited. And then eventually, the Indian plate collided with the Eurasian plate and pushed up, and the marine sediment that was in between them scraped up and piled up on top of those mountains. So the sedimentary strata that was deposited between Eurasia and India eventually uplifted and got folded into the mountains. And when the continental crust portions finally collided, subduction significantly slowed down, and the edge of the Eurasian plate was lifted up as the continental Indian plate wedged underneath it, causing the Tibetan Plateau. And the Indian plate continues to move north, resulting in a continued uplift of the Himalayas. The Himalayas are still getting higher because the Indian plate is still slowly slamming into Eurasia. So here's the Eurasian plate, here's the Indian plate, here's the oceanic crust in between. sediment from the bottom of the oceanic crust got scraped up and piled up on top. The oceanic crust subducted beneath Asia until the continental crusts collided, and the collision of the Eurasian and Indian continental plates resulted in the lofty Himalayas. The Himalayas are basically the highest mountains in the world because they're the youngest mountains in the world. Because the longer mountains stick around, the shorter they get because they steadily wear down. So that was the end of chapter 21. I will go over the review of chapter 21, and then I'll start chapter 22. So the two types of seismic waves are surface waves and body waves. The earthquake waves responsible for the most damage caused by earthquakes are the surface waves. They're on the surface. They have the biggest vibrations. The body waves come in two types. These are P waves and S waves. Primary and secondary is how I believe they were originally named, because the primary ones come first, then the secondary ones come second, because the primary ones travel faster. There also can be considered pressure waves and shear waves, because that is the type of wave they are, which is a nice correspondence. Which type of body wave can travel through solids? Both P and S waves travel through solids. Which body wave can also travel through liquids? Only P waves can travel through liquids. S waves, when they hit a liquid, they basically slide and no wave gets transmitted into the liquid. And which travels faster? P waves are faster than S waves. Hence the reason they are called primary waves, because they arrive first. P waves are the fastest, then S waves, then surface waves. Surface waves come last. The velocity of body waves depends mainly on which physical property of the material they pass through. The primary thing that affects the velocity of body waves is their density, is the density of the material it's passing through. This is actually pretty similar for sound, because P waves are basically sound waves. Denser materials transmit sound faster. So sound travels faster underwater and travels even faster in like solid metal. The four layers of the earth from the surface to the interior are the crust, the thin layer we live on, then the mantle, which is the hot rock layer, the denser hot rock layer beneath the crust, then the outer core, which is the liquid metallic outer core, and then the inner core, which is the solid metallic inner core. The outer core is very important to us because the liquid flow currents in the liquid metal of the outer core are what create the magnetic field of the Earth. All the layers are solid except for the outer core, which is liquid, as I just mentioned, which is thicker continental or oceanic crust. Continental crust is significantly thicker than oceanic crust. It's something like 3 to 4 times as thick generally, or more. It can be as much as, it depends on the thing, but it's always quite a bit thicker. Continental crust is mainly composed of granite rock or things similar to granite, one of the most common materials in it. An oceanic crust is mainly composed of basalt. Basaltic rock in the oceanic crust, granitic rock in the continental crust. We'll talk about what the difference between those is in the next chapter when we talk about different rock types. But yes, continental crust has a lot of granite. Oceanic crust has is primarily basalt. The boundary between the bottom of the crust and the upper mantle is called the Mohorovic discontinuity, or MOHO. The solid rigid layer of the crust and upper mantle is called the lithosphere. The layer that lies below the bottom of the crust that makes up the top of the mantle that is soft is called the asthenosphere. So the solid rigid layer of the crust and upper mantle is the lithosphere. Immediately below that, the softer, more plastic layer is the asthenosphere. The movement of the continents over time from a large supercontinent to the present positions is referred to as the theory of continental drift. The name of the supercontinent that broke up around 200 million years ago was Pangaea. There have been several other supercontinents in the history of the Earth because the continent plates have separated and recombined several times. The name of the scientist that proposed the theory of continental drift was Alfred Wegener. And the evidence for the theory of continental drift is based on biological and paleontological evidence, continuity of geologic features, and the shape of the continents. Those are the three main areas. The theory discussed in the continental drift was not generally accepted by the scientific community because it didn't have a mechanism for the continents to move through oceanic crust. It didn't have a mechanism to describe the movement of the continents. The name of the geologist in the 1960s that used ocean floor soundings to propose the theory of seafloor spreading was Harry Hess. He was able to put together evidence about mid-ocean ridges and such from other scientists and Alfred Wegener's theory of continental drift and propose this model of propose an actual mechanism for the movement of continents. And what has happened to the magnetic field of the Earth several times in the past that's recorded in the rock material bordering the Mid-Atlantic Ridge and other mid-ocean ridges, the magnetic field of the Earth has reversed. That happens every few million years or so. And we have evidence of when it happens because it gets recorded in rocks. So when we have rocks that we can date, like in volcanoes or things, we can figure out when it happened, and then you can see that the same pattern occurs on either side of mid-ocean ridges. Theories of continental drift and seafloor spreading have now been combined into the single theory of plate tectonics, which is older, continental crust or oceanic crust. Continental crust is significantly older than oceanic crust. Most oceanic crust is maybe like less than 200 million years old. All the oceanic crust in the Atlantic is less than 180 million years old or something like that. I'm not so sure about the Pacific. It might have some older crust in it, but generally oceanic crust is less than about 200 million years old. There are parts of the continental crust that are like 3.5 to 4 billion years old. And how many plates are thought to exist? About 20. Most volcanic and earthquake activity occurs at the borders between plates. The three types of plate boundaries are divergent, spreading apart, convergent, coming together, and transform, sliding side to side. The layer that the Earth's crust rides on is the asthenosphere. Plate movement is believed to be caused by convection currents in the Earth's upper mantle, where warm material rises, travels to the side, and then travels to the side, cools, and sinks. Two plates moving apart is referred to as a divergent boundary. At a divergent boundary, the youngest rock is found near the boundary, not further away. Your newest rock is at the boundary. It's older as you travel further away from it. Two plates moving towards each other is referred to as a convergent boundary. The three types of combinations of plates moving towards each other are oceanic-oceanic, oceanic-continental, and continental-continental. And the plate combination that doesn't show much subduction is continental-continental because the continental crust is just too thick and too light. neither thick lump of continental crust sinks. They just bend and fold. The type of crust that is always the one that ends up subducting is oceanic crust. Deep sea trenches usually form during which type of plate combination? Either oceanic or oceanic continental. Both form trenches. The combination of plate movement that usually results in very high mountain ranges, such as the Alps, is continental collision. And the type of plate boundary that involves plates moving past each other is a transform plate boundary. Most of the volcanoes that we talk about form at convergent plate boundaries. There are plenty of volcanoes at divergent boundaries, but the vast majority of them are underwater. So we don't really think about them that much. Most earthquakes form because of the movement of plates at fault lines, movement of plates relative to each other. A fracture of rock caused by the visible movement of plates is called a fault. The longest fault systems are usually at transform plate boundaries. Just because they're sliding against each other, you get really nice long faults that way. The actual point in the Earth's interior where an earthquake originates is called the focus or the hypocenter. But this book always refers to as focus, so in the questions it'll be called the focus. And the point on the Earth's surface directly above the origin of the earthquake is called the epicenter. So the focus is underground. It's where the earthquake actually starts. The epicenter is the point on the surface directly above it, where the first effects of the earthquake hit the surface. The device used to detect and measure earthquake waves is a seismograph or a seismometer, but I believe what we call a seismograph. The earthquake scale that measures earthquakes by the energy they release is the Richter scale. The earthquake scale that measures earthquakes by the damage they cause is called the modified Mercalli scale. An earthquake on the ocean floor can create giant waves called tsunamis. Mountains are usually formed when the crust is deformed through folding and faulting. And arch-shaped faults are called anticlines. Trough-shaped faults are called synclines. The kind of fault that forms when two sides of a rock formation are pulled apart is called a normal fault. When two sides of a rock formation are pushed together, that is the reverse. It is a reverse fault. And when they slide by each other, that is a transform or strike-slip fault. And I believe earlier I called the mixture of fault types a dip-slip fault, which is incorrect. It's actually called the hybrid fault. Normal and transform faults are technically called dip-slip faults because the slip is in the dip direction. But normal and reverse faults are called dip-slip faults, but that's not important. You don't need to know that term. Besides being formed from faulting and folding, mountains can also form from volcanoes. So that was chapter 21. We still have a bit of time, so I will start up chapter 22. So we talked about the large scale structure. The Earth. Now let's talk about stuff on a smaller scale. Let's talk about minerals, rocks, and volcanoes. So we'll start by defining the characteristics of minerals, so you can know what a mineral is and what things are minerals, what things aren't. We'll describe how minerals form from magma and other solutions. We'll talk about the physical and chemical tests that can be used to identify minerals. We'll discuss how to use crystal form, luster, hardness, cleavage, and fracture, streak, special properties, texture, and density or specific gravity to identify various minerals. We'll go over and give examples of common mineral groups, including silicates, carbonates, and oxides. We'll describe the usefulness of various minerals, including ores and gems. We'll look at the various processes involved in the rock cycle and discuss the conservation of matter during formation, weathering, sedimentation, and reformation of rock materials. We'll describe how the composition of magma influences the formation of igneous rocks, and we'll go over the factors that influence how igneous rocks melt and crystallize. We'll describe the different types of igneous rocks in terms of mineral composition and texture, and describe the relationship between magma cooling rates and the size of grains that form in rocks. We'll describe shield, cinder cone, and composite volcanoes in terms of their formation and type of eruption. We'll describe the type of magma found in volcanoes and how the magma type influences volcanic eruptions. We'll describe the role of pressure and dissolved gases in volcanic eruptions. We'll look at the type of material expelled during a volcanic eruption. Then we'll look at the processes involved in the formation of sedimentary rocks, the main structural features of sedimentary rocks, and how these features can provide clues to of past life on Earth. We'll look at the formation of clastic or inorganic sedimentary rocks in terms of grain size. We'll look at the formation of chemical and biochemical sedimentary rocks. And we'll look at the various types of metamorphism involved in the formation of metamorphic rocks and the characteristics of foliated and non-foliated metamorphic rocks. Now, looking at identification of minerals and talking about crystals and such, I can suggest the anime Rare Rocks. It's currently on Crunchyroll. It was, when I put this up last time, it was still airing, but it's completed its run. It's called Ruri no Hoseki in Japanese. It has an excellent description of the processes by which minerals form and move. But it's mostly focused looking at, crystals. Like Ruri no Hoseki actually means like Ruri's jewels. But yeah, it has some really good geology in it. Though it is focused on the geology of Japan because it's set in Japan. Japan has, lots of active volcanism and such, which changes how the geology works compared to, say, here. So in this chapter, we're going to largely talk about rocks and minerals. And we'll talk about the difference between what a rock is and what a mineral is. Basically, rocks are made of minerals. And minerals are the components we use to make rocks, but a rock isn't necessarily made of all the same mineral. There can be several different minerals in a rock, and commonly are. And we'll see that specific rocks and minerals form in response to a myriad of earth processes. And that means that the existing rocks and minerals we find can be used to determine past geologic events. Because we can know if these rocks exist, these processes must have happened, which means these conditions must have existed in the past. So let's talk about what a mineral is, how a mineral is defined. So a mineral is defined as a naturally occurring, so it has to happen naturally. So if I make it in a lab, it's not a mineral. Inorganic, crystalline, solid substance consisting of one or more chemical elements in fairly specific proportions with a distinctive set of physical properties. So technically, this also means stuff that it's a little bit, the inorganic bit, it's a little fuzzy, but generally we think about material that's created from living things as not being a mineral. So coal, which is made of wood that has been converted into carbon, is not a mineral technically, because it comes from an organic source, and neither is amber. Well, I don't think amber is also might not also be crystal. The other thing is that it has to be crystalline. It has to have specific crystal structure. So there are, so like obsidian, which is volcanic glass, doesn't have a crystalline structure. And because it doesn't have a crystalline structure, obsidian is also technically not a mineral. So it has to be a naturally occurring inorganic crystalline solid substance that consists of one or more chemical elements in fairly specific proportions with a distinctive set of physical properties. Now, minerals are around us all over the place. Some are quite valuable. Diamonds, sapphires, emeralds. Other minerals are very common. Things like calcite, quartz, ice. Ice is technically a mineral. If you make it in your freezer, it's not necessarily, but yeah, the ice outside, that's a mineral. And it does mean that rivers flow with magma based on technical definitions. And then mineralogy is the study of minerals. Sometimes we seek out specific rocks as being rich in certain minerals that are useful to us. An ore, like iron ore, gold ore, or copper ore, anything that is classified as an ore is a rock or that has a commercially viable, valuable amount of some type of element or mineral in it. And that means modern economics determines what's an ore or not. So something technically can stop being an ore if it becomes no longer commercially viable to extract that mineral from it. And something can become an ore if it suddenly becomes more commercially viable for extracting that. But that's sort of the general idea. So here are some examples of some rock-forming minerals. So this is olivine, which is sort of ultramafic, deep rock, somewhat similar to what you'd see in the mantle. This is calcium flagellate feldspar. This is halite. That's rock salt. Halite is the mineral name for salt. So your table salt is artificial halite. Pyroxene, sodium flagellate feldspar, gypsum. Gypsum is the mineral we use to make drywall. Gypsum gets used in a lot of stuff in construction. There's amphibole. There's biotite muscovite, which are micas that form nice thin sheets of hair. There's orgiclase feldspars. Feldspars are the most common mineral type in the world. There's quartz. Quartz is just pure silicon dioxide. It's very common because it's sort of silicon dioxide is sort of the base material for most of these minerals. There's limonite. There's hematite. Hematite is an iron ore.
Is deep slate technically a mineral? Like
so slate is a rock.
Okay.
Made of several types of minerals. Deep slate is a piece of terminology I think they made up for Minecraft because they wouldn't put slate deep underground.
I mean,
dark rock.
Well, it's like a form of like.
But slate is a type of
like
rock.
It's
We'll
deep
talk about.
Volcanic, like
Yeah.
Underground.
So slate is a type of metamorphic rock that forms from other rocks, and it does form deep underground. There may be technically a deep slate, but I thought that was something that specifically deep slate.
Maybe I was thinking of just slate.
Slate is a real rock. You can get it. You can make your roof out of it. I think they added deep for Minecraft because they were particularly putting it deep underground.
I just don't remember where I heard
And then
from that, but
and then calcite. So calcite is the primary mineral in limestone. Now, 8 chemical elements are the major constituents of most of the minerals we find on Earth. The most abundant elements in Earth crust are these. These are in order of abundance, I believe. The most abundant element in the Earth's crust is oxygen, followed by silicon. And the biggest type, the most common type of mineral are silicate minerals. Silicate minerals are formed of primarily oxygen and silicon with some other stuff. So oxygen, silicon, then there are things like aluminum, iron, calcium, sodium, potassium, and magnesium. So aluminum is quite common, iron is quite common, calcium is common, sodium is common, potassium and magnesium are also common. Well over 2,000 minerals have been identified in the Earth's crust, but some of those are super rare. Like there's some minerals out there that are only found in like one place on Earth. Only about 20 of these are common. I think they're up to like 5,000 or something. There's a lot of minerals that have been identified, and less than 10 minerals account for more than 90% of the Earth's crust by mass. So there's a handful of very common minerals and a lot of not very common minerals. So here, almost half of the Earth's crust is made of oxygen by mass. 47% oxygen, 27% silicon, 8% aluminum, 5% iron, 3.5% calcium, 3% sodium, 2.5% potassium, 2% magnesium, and then 82 other elements make up the other 2%.
Oxygen really that feeling. Like when you talk about
Well,
mass,
almost every mineral is oxygen plus something else.
is that how they influence?
I mean, so oxides of various sorts form the primary building blocks of most minerals. Oxygen is, so in the universe, oxygen is pretty common. And it reacts with stuff very well. It's very reactive. So what happens is you get oxygen reacts. So when you find aluminum oxides. When you find iron oxides. Or you find silicon and oxygen together and bits of all these other ones. Is the most common way you find these things. But like, you find, all of the iron ores have various iron oxides in them. That's, for example. So most minerals that form crustal rocks have significant amounts of oxygen and silicon. So when you think rock, what you're usually thinking is some sort of silicate mineral. So the mineral quartz is silicon dioxide. It's entirely composed of oxygen and silicon. And it has the chemical formula SiO2. And it has this three-dimensional lattice structure, which makes it quite strong. Quartz and many other minerals that contain oxygen and silicon are called silicates. And silicates are the most abundant family of rock-forming minerals in the crust. So the other thing is that, we're talking about the crust here. Heavier stuff tends to sink. So the core, for example, is primarily iron and nickel. Not nearly as much oxygen and silicon. While the mantle is got less oxygen, less silicon in it, and more heavier elements like iron and magnesium and things. So here is a video about what's the difference between gems, minerals, crystals, and rocks.
What are minerals, rocks, crystals, and gems? What's the difference? Well, to start off simply, rocks, crystals, and gems all can be made up of minerals. So what the heck is a mineral? A mineral is a solid made by the natural activities of Earth, like lava spewing out of volcanoes or water dripping down through cracks in caves. Fluorite, gold, and calcite are just a few mineral names you might recognize. Minerals are made up of elements elements that come together in a regular, specific pattern. These geometric groups of elements are the building blocks of a mineral. A crystal of that mineral forms when these building blocks stack on top of one another, repeating their arrangement to form a three-dimensional object with flat faces. Quartz, for example, has a crystal structure made of oxygen atoms and silicon atoms that repeat in a shape that looks like a rhombus. The shapes that these chemical building blocks take are different from mineral to mineral. Sometimes, two minerals can be made of the same elements, but with different building blocks making up their structure, like diamond and graphite. The large geometric shapes and flat faces we see in crystals reflect what happens when these building blocks repeat over and over again. Now let's move on to rocks. A rock is a solid object made up of mineral grains, but it can have many different minerals inside it, and you don't see the same repetitive shapes that you see in crystals. Granite is an easy example. You can see the different grains of many types of minerals making up a piece. Limestone is also a rock, even though it's usually made of mostly one mineral, calcite. But limestone is made of calcite fragments mashed all together, and a calcite crystal has order and a geometric shape. So where do gems fit in? They have a geometric shape, and many look like crystals, right? But really, gems are minerals or stones that have been cut, ground, and polished by people to enhance their beauty. A finished gem may look very different from the original mineral it was carved from. Many times, gems are shaped with different flat faces to catch and scatter light. They aren't always minerals either. They can be made of things that come from animals and plants, like pearls or amber, or they might even be man-made in a lab. Let's make like a crystal and repeat that one more time. Think about pyrite or fool's gold. Pyrite is a mineral made of iron and sulfur. Those elements come together in the shape of a cube and repeat to form a pyrite crystal. These crystals can get so big you can see them with your naked eye. Other times, the pyrite crystals are just flecks in a rock like slate. And if it was cut and polished with flat faces, it would be considered a pyrite gem. So there you have it, crystal clear. The difference between minerals, gems, rocks, and crystals.
And I think I'll stop there for today, and we'll continue with talking about silicates. But yeah. So yeah, if you see a gem, that's not necessarily cut in the shape of its natural crystal structure.